Welcome to our presentation for the group assignment for forecasting Math 1307. We chose to complete the competitive project, which entailed a dataset of 303 time series taken from the original M3 competition held in June 2017. The dataset contains 303 time series that has monthly, quarterly, and yearly data. The steps that we followed were converting all the 303 given time series into time series objects in R, which we were subsetted from the original M competition data that covers areas such as microeconomic, macroeconomic, industrial, financial, and demographic information. The provided project dataset was comprised of 101 monthly, 101 quarterly, 101 yearly time series. As such, we began by first creating a function which read each time series into R according to its frequency and to also account for seasonality. The output of this function appended all time series into a single list. The separation is needed to account for seasonality in particular state space models and to achieve a return list consisting of all the data. Originally, we subsetted 95% of each time series into a training set and the remaining 5% as a test set, which we would be used to forecast on. However, this was problematic as we had a range of data points per series ranging from 20 to over 150. For the series with smaller amounts of data points, using 5% of the series didn't provide enough data points to forecast on, being 6, 8, or 18 times ahead as outlined in the spec sheet. As such, we instead created an algorithm which separated each series into their training and test sets according to the required forecasting length. In other words, we took 6 points out to forecast on for yearly time series and 8 and 18 points for the quarterly and monthly series respectively. We then created a function to apply all combinations of exponential smoothing and state space models. In the case of non-seasonal models, we specified the function to apply combinations for additive and multiplicative factors for both error and trend, damped and undamped options for trend, and set seasonality to neutral. The function returned a list of all possible combinations for each model and its respective MAC, AIC, and BIC values. For the seasonal data, we used the same function but with minor alterations. We specified the function to include additive and multiplicative factors for seasonality. Forbidden models such as AMA, MMA, AAM, AMM, AMN, and ANM were excluded from the function for both seasonal and non-seasonal series. Expanding on this algorithm, we used Shapiro-Wilk and Young-Buck's significant tests on residuals which were included in the output. Firstly, for each time series, the Shapiro-Wilk test was applied to models for distributed errors. Those that passed this Shapiro-Wilk test were then tested for autocorrelation in the errors using Young-Buck's significant test. The models that passed both tests then sorted by their MAC values, and the model with the lowest MAC was selected as the optimal model for forecasting. First, Shapiro-Wilk test was used to test for residual normality, where alpha is equal to 0.05, and Young-Buck's significant test was used to test for residual autocorrelation at lag 1, where alpha is equal to 0.05. An important aspect of this function was to deal with models that did not pass Shapiro-Wilk test. In this case, the function continues to apply Young-Buck's significance test on all possible models combinations of the series. The optimal model is selected based on the model that passes Young-Buck's significance test and has the lowest MAC value. In cases where all possible model combinations of a series don't pass the Shapiro-Wilk nor the Young-Buck's tests, where p-value is bigger than 0.05, the function selects the optimal model purely based on the model with the lowest MAC value. Here is an example of the data frame produced by the function. We have the best model selected for each time series the MAC for the both training and test sets. The result of Shapiro-Wilk and Young-Buck's significant tests and the category of the data series. In this format, it's very easy to produce a summary table for the statistics of interest. This is our summary table, which shows a tally of how many models passed or failed the residual significance tests. It's easy to see the differing results between the test and training set. Closer inspection of the MAC values for the optimal models showed that the training set was consistently more accurate. This is most likely due to the training set having access to larger sample sizes for modeling. However, it's important to note that the yearly data sets had the lowest sample sizes, which could explain the bigger difference between the test and training set MACs when compared to the monthly and quarterly data sets. Moving on to the residual tests themselves, it seems like the Shapiro-Wilk test for normally distributed errors had lower pass counts in comparison to the Young-Buck's significance test for autocorrelation. It is possible to any sort of large variation or intervention within a series would result in a non-normal distribution, hence causing the Shapiro-Wilk test to be sensitive. However, it's interesting to note that Young-Buck's significant tests performed very well, suggesting the state space models were able to capture serial correlation in a series consistently. An algorithm was also created to forecast using the selected optimal model for 6, 8, and 18 data points ahead for yearly, quarterly, and monthly series respectively. Each model's accuracy was based on the MAC of the forecast, and this value was stored in our output data frame, which also included the specification of the optimal model, i.e., additive, multiplicative, or neutral factors, and the significance test results for the Shapiro-Wilk test and Young-Buck significant tests. Here we have a visual summary of our models for the monthly series. You can see most of the monthly data was fitted to MMM damped true model, and we had 72 models pass the Shapiro-Wilk test, and 99 of the 101 models passed the Young-Buck's significance test. Overall, there were relatively low MAC values for both the training and the test data sets. However, the range in MAC was larger for the test set. This is the visual summary for the quarterly series. Most of the quarterly series were fitted to MAM damped true model, and this time we had 87 models pass the Shapiro-Wilk test, and all of the 101 models passed the Young-Buck's test. Generally, the MAC values were also low for the quarterly models, only slightly higher than the monthly models. Finally, we came to the visual summary of the annual series. MMN damped true model was the most common model fitted, with 92 of the models passing the Shapiro-Wilk test and 100 of the 101 passing the Young-Buck's test. The MAC values for both the training and test sets were higher than the previously quarterly and monthly series. Here we have a flow chart which outlines the process of model selection and the various functions used. A quick summary of the overall process could be outlined as: all series were read into a list. Each series was then separated into training and test sets. Each set was then modeled with all possible state space models. Residual tests were performed within the modeling process. Models were then filtered according to MAC, Shapiro-Wilk, and Young-Buck's tests. Final data frame summarizes the findings in regards to overall MAC, Shapiro-Wilk, and Young-Buck's tests that passed. And this concludes our presentation. Thank you for listening.